Welcome and Namaste. In the last two of my lecture videos, I have given the introductory marks on the Advanced Physical Chemistry course, the brief outline of the Unit 2, the Electrochemistry and Fundamentals of X-ray Crystallography. In this lecture, I would like to start with what is called as the actual syllabus from Unit 3, the Fundamentals of Crystallography. Let me begin with the fundamentals of the crystallography, that is named as Module 1. In the Module 1, the concepts I am going to introduce is law of interfacial angles and law of symmetry. These two concepts I will be introducing in this lecture. Let me take up the law of interfacial angles. This law of interfacial angles is one of the important laws and first laws of the crystallography. The concept of law of interfacial angles began in the year 1669 by Danish physician Nicolas Steno, and he named it as Steno's laws and the first law of the crystallography. And this law was also supported by Domenico Guglielmini in 1688, and later it has been scientifically verified by, finally, Jean-Baptiste Rome during 1783. How the Steno did his observation? He is also a mineralogist. He was working with the minerals. He found his observations with the quartz crystals, as I shown in the picture. The same species, the quartz crystals, the shape of these crystals are varied. And also you look at the pictures of the quartz crystal, the sizes of the quartz crystals also vary. So, for a particular mineral or for a particular compound of that crystals, or the crystals are belonging to that compound or that species, during the crystal growth, the size and shape of the crystals may be varied. But as the crystal do exhibit at different phases, where the angle between the phases remains the constant. That was his observation for the first time. And this was also supported by Guglielmi with the same quartz crystals. And the Steno has also proposed the same law with this observation. And Jean-Baptiste Rome in 1783, as who has seen many of the quartz crystals, the shapes of the crystals which are shown on the picture of the right hand side, he has scientifically calculated with the device called as goniometer. And finally, the law is stated as the law of the constancy of the interfacial angles. What this law says that, it states that the angles between the crystals of a given species are constant, irrespective of the lateral extension of these faces and the origin of the crystal. All these are characteristic of that species. Here the species means a particular kind of a mineral or a compound. The crystals of that compound, irrespective of its origin, either it is a natural origin or it is a synthetic origin or a artificial origin. As I said, during the growth of the crystals, the size and shape may be vary. Hence, there may be an extension of the faces as the size may be increases. There may be a face maybe increases or some faces may be decreases. Size of the faces may be decreases. But the angles between the crystal faces of that species remains a constant. This is called as the law of the constancy of the interfacial angles. Means that there is a consistency in the angles between the faces. I will show you that suppose for a particular species, the crystal shape may be this. This is one face and this is another face. The angle between this face is called as the interfacial angles. Suppose the angle is 120 degrees. What I do is, during the growth of the crystal, one crystal shape may be this and another crystal shape may be like this. Right. That is what, as I said, there is a lateral extension of the faces. The size of the faces may be decreases or increases. They are vary. But the angles is again 120 degrees. Right? Suppose I will take another picture. If there is a type of the shape of the same crystal, maybe like this. Again, the angle is 120 degrees. See here, the shape of this, shape of this, shape of this of the same crystal. But the angle between the faces remains the same. That is what consistency in the angles between the faces is called as the law of consistency of the interfacial angles. This is all about this law. And secondly, the next concept is the law of symmetry. This law of symmetry, the concept of symmetry has studied in detail earlier, that is the molecular symmetry and group theory. Any objects in the nature do exhibit this wonderful property called as a symmetry. Any number of objects or any different type of objects do exhibit a same amount of symmetry. They will be grouped together. That is what the unified group. And this symmetry, why it is being introduced into the crystal system? Why the concept of symmetry is needed for the study of the crystallography? As I said in the beginning of the classes, the basics classes, the crystals do have a definite geometry, either cubic, primitive cubic, face-centered cubic, or body-centered cubic, orthorhombic, monoclinic, triclinic, hexagonal. Any type of these geometries or the system they may exhibit. These geometries do have high degree of symmetries. Hence, the symmetry property should be exhibited by a crystal because the atoms in the crystals are perfectly arranged. Therefore, without this symmetry, the crystals cannot be classified extensively. So, the symmetry is highly needed to study the crystallography. So, what is this law says? All crystals of the same substance possess the same elements of symmetry. Yes, all crystals of the same substance. Say, for example, sodium chloride, which is belonging to the face-centered cube. Any crystals of the sodium chloride should exhibit the same amount of the symmetry elements or same kind of the symmetry elements. Say, for example, cesium chloride, which is a body-centered cube. Any crystals of the cesium chloride body-centered cubic structure do have the same number of symmetry elements. That is what all crystals of the same substance possess the same elements of symmetry. Now the question is, just I will give you a revise. What is called as symmetry? Then what are the types of symmetry elements? And how many crystal systems are being classified based upon the number of symmetry elements is considered. So let me start with what is called as a symmetry. Symmetry is, the name itself indicates symmetry, the similar measurements. That is what a state in which the parts on opposite side of a plane, line or point display arrangements that are related to one another via symmetry operations such as translation, rotation, reflection or inversion. This translation, rotation, reflection or inversion or operation, you are doing some manipulation to the object. Either you can rotate or reflect or inversion. Through what? Through a plane, through a line or a point. This plane, line or point are symmetry elements. Therefore, I will explain this, what is called as a plane, what is this line or what is this point. So, based upon the presence of a line in a molecule, the symmetry element generated is called as axis of symmetry. And what is this axis of symmetry? I will explain what is axis of symmetry. This is also called as a line of symmetry. Suppose I have an object like this, a sphere you can take, right? I will take a sphere. I will draw an imaginary line through the passing through the center of the circle. It is a two-dimensional. I cannot exactly give you a picture. How do you imagine that? There is a circle. Through the center, you are passing a line. Through that line, what I do that, you do a clockwise rotation. So imaginary line passing through the center of the sphere. With that line, you are assume that it is rotated to 10 degree. After doing a rotation of a 10 degree through that line, what is the next appearance? How the ball looks like. Before rotation, how the sphere was looking like. After the rotation of 10 degree also, it looks the same appearance. I do a 30 degree rotation, it looks the same. I do a rotation by 50 degree, appearance same. Because this sphere is a spherically symmetrical. Right? Spherically symmetrical. But I will take at this triangle. Assume that there is a center point here. And I will draw an imaginary line passing through this center. Right? I do the clockwise rotation. I will name this face as side as 1, this is 2, and this is 3. Right? Now, assume that that axis or a line passes through the center. Through that, I am start rotating a triangle. Suppose if you are rotating it by 90 degree. Can you get the same appearance as in the original? Never. I will do it by 80 degree. Never you will get the same appearance. It will give you the same appearance only when you are rotating it through the 120 degree. When you are rotating it through 120 degree, this 1 goes to 2, 2 goes to 3, and 3 goes to 1, and it looks the same appearance. Then, if you are rotating 120 degree thrice, again it will 1 comes on 1, 2 takes its original position, 3 takes its original position. So, how many times you can rotate it to get the original position 3 times. So 3 times you are rotating through an angle of 120 degree. Therefore, 360 by 120, that gives you the number 3. Therefore, what you have done through this line, you are doing rotated. Therefore, this axis, this line of symmetry is called as axis of symmetry. What you have done the rotation. Therefore, in the shoe and fly system, it is called as C3 rotation, right? Similarly, 180 degree. Suppose I will take a square here, right? It demands if I draw a line passing through the origin, right? It demands you to rotate by an angle of 90 degree, and therefore it is called as C4 axis of symmetry, right? Because the angle is 90, right? Only when, suppose this is 1, this is 2, and this is 3, and this is 4, when you do a 90 degree rotation, 1 goes to 2, 2 goes to 3, 3 goes to 4. Again you do a rotation, and similarly the sides will changes and it gives you the same appearance. You will get a original configuration only when after C4 rotation, that is 360 of every 360 degree rotation, it gives you the original configuration. So what is this C3? C3 is an axis of symmetry called as C3 axis. And what is this 90 degree rotation? C4 axis. Similarly, C6, C7, C2, C1, like, right? Suppose if there is a molecule like this, right? There is a carbon, asymmetric carbon, A, B, C, D. This is total unsymmetrical molecule. I will pass a line, right, through the center, and I will do the clockwise rotation, right? Only with the rotation of 360 degree, you are going to get a original configuration. It means that since it is totally unsymmetrical molecule, therefore, to get the original configuration, you do only 360 degree rotation. Therefore, it is called as C1. So this is all about axis of symmetry. With the axis of symmetry, what you can do is you can do the rotation. Then what is a plane of symmetry? The plane of symmetry is a very simple concept. Suppose I will take a square here, like you can take a cyclobutane molecule, right? And what I do is I will pass a line passing through the center, and you do what? Right? Line. That line acts, which bisects this square into two equal halves, right? This is a vertical plane where this part, suppose this part is A and this part is B, this part is a reflection of this, and then that is called as a plane of symmetry. Then this is called as sigma, you know that. And similarly, right, you know about the center of symmetry, right? Suppose I have a square like this, right? Right? Suppose there is one center atom here, maybe B, and here is A, and here is A, and here is A, and here is A, right? From this center atom B, you draw a line on opposite, exactly opposite side of this, which meets the same atom. Then again this also do the same. Then this point is called as center of symmetry or center of inversion. When you do invert, suppose this is A1, this is A2, this A1 goes to A2, A2 goes to A1. Suppose this is A3 and this is A4. After inversion, that is center of symmetry, A3 goes to A4, A4 goes to A3. If this condition is being satisfied, what is the condition? From the center, if you extend a line on opposite side, it should meet the same atom or the same side. Then this object do exhibit a center of symmetry, and that center of symmetry is called as inversion center. You know that already. This is Cn, this is sigma n, this is inversion. And other two symmetry elements are called as improper axis of symmetry, and other one is called as identity element, that is doing the full operation. Here in the crystal system, the same thing follows. You know, already in undergraduate study, you have studied about the crystal have exhibited a cubic type of geometry, right? This cubic type of geometry do exhibit 11 proper axis of symmetry. That is C3 axis and C4 axis. C3 and C4 axis. And what about the plane of symmetry? There are total 9 plane of symmetry it is exhibited, right? And there is one center of symmetry. Yes, I am not showing in detail, but I am giving you the concept that if the crystal do have a exhibiting the cubic type of geometry, then how many symmetry elements are it is presenting? 11 proper axes of symmetries, including C3, C4, and C2, and 9 plane of symmetry, including horizontal plane and vertical planes, and one center of symmetry. So there are totally 23 symmetry elements which are being present. So therefore, since you know this concept, the cubic geometry has a 23 symmetry elements. Means each crystal of a given species or a given compound which is belonging to the seven crystal system may exhibit a certain kind of symmetry elements. So the existence of the symmetry elements may be varied from one type of the crystal system to the other type of the crystal system. Therefore, based upon the existence of the symmetry elements contained in a particular crystal structure, the crystals are being classified. That is the reason why the symmetry concept is very, very important. So this is already, you know, that 2 fold axis, 3 fold axis, 4 fold axis, 6 fold axis, and therefore the crystals are being classified based upon the existence of the symmetry elements. As you know, there are 7 crystal systems. Then further it is classified into 14 Bravais lattices, and further based upon the symmetry elements, it is classified into totally 32 symmetry point groups of the crystals. Out of these 32 point groups, and finally, there are, based upon the number of symmetry elements variables, it is finally 230 space groups. So, if you are generated a crystal today, that crystal geometry maybe comes in any of the 7 crystal system and fall into the any one of the 14 Bravais lattices, and maybe fall into any one of the 32 point groups, and finally it should fall lie in any one of the space group out of 230. So the combination of all available symmetry operation, that is 32 point groups, as you already studied, Cn type of point group, C2V type of point group, C3V type of point group, DNH, DND, all these point groups you have studied, but that is the naming of the point groups from the shoe and fly system. But in the crystal system, the same symmetry elements existed in the crystals. Then these crystals are being given the different type of the symbolic system called as Hermann-Morgan. You know, that is what it is given in the chart. That is, the international table lists those by symbols and numbers. Say, for example, here a crystal system is there. There is a triclinic, and the international system, it can be written as 1. And shoe and flies, you know that if there is C1 axis of symmetry, it is belonging to C1 point group, then it is written as C1. But in space group with the crystal system, it is named as P1. And similarly, CI type of point group is belonging to triclinic type of geometries or a crystal system, and it is symbolized, the space group is belonging to P1. And similarly, if the monoclinic crystal system, there are 13 space groups are present, and it is named as M, and it is CS. There is only one plane. You know that the CS point group, the CS point group is having only one plane, that is called as CS type of. But in Hermann-Morgan system, it is called as PM or PC or CM, CC. There are total 4 space group. And again, in the second type of monoclinic system, 2 by M, Yeah, there is a rotational axis is order of the rotational axis is 2, and H, if there is a plane of symmetry, horizontal plane, then the point group is called as C2H. But this, the same C2H can be symbolized as P2 by M, P21 by M, C2 by M, P2C, P21C, C2C. These are all different space groups symbolized for C2H point groups. If the suppose the crystal is of monoclinic, and it may also exhibit these kind of, based upon the symmetry operation, these are classified into these space groups. Similarly, orthorhombic, tetragonal, trigonal, hexagonal. Look at here. Here it is started from first space group, ended with all these 7 crystal system. There are 230 space groups. So this is the chart where it shows you the very, very important chart where it shows you there are 230 space groups in the crystal system based upon the existence of the symmetry elements and various symmetry operations possible for a particular type of crystal system. Okay, and in this lecture, I have explained about the law of interfacial angles and law of symmetry. Hope all these points are very clear to you, and we shall meet in the next class, next module 2, where I am going to introduce the concept of Miller indices along with some of the problems on Miller indices. Okay. Once again, I hope that you have understood what all we have covered in this lecture about the law of interfacial angles and law of symmetry. Have a nice time.